we've seen Dijkstra's algorithm, we've seen an example. Now we actually have to prove the correctness of Dijkstra's algorithm. Now many of the key ingredients that prove the correctness of Dijkstra's algorithm, we actually have seen them before with Prim's algorithm. Just, we're going to need the right invariant to make this work though. So the first thing I have to do is convince you that this is actually going to be producing a spanning tree. The second thing is that whenever I introduce a vertex into the blob, that the path that I get by extending an edge to this vertex, the one for which the blob will use to devour that vertex, it has to be that that itself is a shortest path. First, I got to convince you that this algorithm does produce a spanning tree. So, as with Prim's algorithm, Dijkstra's algorithm constructs a spanning tree T as it selects n-1 edges, where n is the number of vertices, implicitly. So previously I discussed how this edge would appear in my previous lesson about Dijkstra. Implicitly. And the algorithm always extends an edge in T, so meaning I bring in another edge that grows the tree in T from inside the blob to outside the blob. Creating no cycles. So there's going to be no cycles. So we know that we're going to end up at the end of the day with a spanning tree, just like in Prim's. It's just that the structure of the spanning tree we get isn't going to be a minimum spanning tree. We want to show that it's a shortest path spanning tree of the source S. So that's what I have to show you. So one thing I really want you to observe, so this is an important observation that's going to play a key role in the correctness of this, is that each vertex V in the set of vertices is DQ'd from the priority queue Q and joins the blob capital B. So we know that each one is going to be, leaves the priority queue and goes into the blob, right? So this is an important fact. So this is going to happen with all the vertices. So what I need to do is show you that each time when it joins the blob, that it has to be the case that when I extended that edge to this vertex that comes out of the priority queue and joins the blob, it's just hungry for that blob. It's just saying, hey, bring that one to my mouth, okay? It has to be that it is, in fact, the shortest distance from that vertex to the source, the orifice of the blob, okay? So just as a little bit of notation for us, for any pair of vertices, U and V in the set of vertices, we're going to call DUV is going to be the length be the length of a shortest UV path, which we'll colloquially just call this the distance from U to V. So if ever I say the distance from U to V, it's always going to be the length of the shortest UV path. As a remark, just for the sake of completely defining this object for you, is if I write duv is equal to infinity, it just simply means there is no path. There is no UV path. That's what it means. So that brings us to a theorem that's going to be the one that we're going to use to prove the correctness of Dijkstra. So I'm just going to keep Dijkstra's algorithm up here. And now we have all the bits and pieces for this theorem. So we know we're going to end up with a spanning tree. And we know that each vertex is going to get DQ'd from the priority queue and it joins the blob. So what happens when that vertex joins the blob? That's going to be the big thing that we need for the correctness of this algorithm. Now, this isn't the only way you could prove this. This is just one such way. So here's a theorem. In Dijkstra's algorithm, when vertex V of G joins the blob, when it joins the blob, it has to be that V dot D is equal to the distance from S to V. That is, V dot D is the length of a shortest path. Length of a shortest path from S to V. And we have computed a shortest SV path. That's the theorem that we're going to be proving. Again, we're going to be coming to our best friend, contradiction. And here's sort of the setup that we have. So we're going to consider when V joins the blob, and I would like to show you that it is in fact going to be the true shortest distance from S to V. What does it mean if that isn't the case? That means that there has to exist, so this has to be true for all the vertices, right? So that means that there is some vertex where this isn't satisfied. Recall that if it was the case that V dot D was less than this, that wouldn't make any sense because, one, Dijkstra's algorithm always picks the one that is closest to the source, the next closest vertex to the source. Likewise, to compute a shorter path than the shortest path, we get back to the same issue we had about, oh yeah, presuming that there is a shorter path than the shortest path. That just doesn't make any sense. So now that we have the game plan, let's get started. So assume otherwise. So assume otherwise. Then there is a vertex V, such that V dot D is strictly bigger than the distance from S to V, right? Now, we want to figure out when this first happens. So I'm going to give this vertex V a name. So I'm going to say, hey, look, we're going to see where the first time this mismatch happens, when Dijkstra goes wrong in the hypothetical here, okay? So remember, we're assuming this such that we can derive a contradiction. So we're going to let Z be the first vertex, the algorithm pulled into the blob B such that so let Z be the first vertex the algorithm pulled into the blob B such that Z dot D is strictly bigger than the distance from S to Z. Very important. I want you to pick this up, put it behind your ear and say, I'm going to come back to this. I'll come back to this. So just remember this fact about Z. Remember this fact about Z. So just to be very clear with you. So it has to be that Z was the first incorrectly picked vertex by the algorithm, where when this algorithm selects this edge, it extends to Z. So it selects an edge to get to Z, but that doesn't result in the shortest SZ path. So it means that there has to be a different SZ path too, right? So graph G is connected. So there exists a shortest SZ path. I'm going to call this P in G. So it's going to be the shortest SZ path. So I'm going to draw us a fun picture. I must stress, the picture isn't the proof, but so here's S. There's Z. Imagine it goes on some, so this is path P here. And imagine that there's the blob. And I'm going to stress that Dijkstra, the way the blob is formed, it need not be the case that all of this path is in the blob, right? If it was, then it would be a part of this path, right? But it isn't. This is a different path than the one that gets picked by the algorithm. So what we're going to do is we're going to consider the moment that the blob devours Z, meaning that it picked it. So I want you to keep in mind the situation here. So the algorithm is what's controlling the blob, right? However, this is the shortest SZ path. And it need not be the case. And keep in mind, it doesn't have to look exactly like this either. It's just the point is that there will be some vertex that's probably not in the blob, right? There's going to be at least one. So consider just when Z joins the blob B, and let Y be the first vertex in P, starting from starting from S to Z, that is not in B. So we follow along this pathway and we find our first vertex that is not in the blob. This is Y. You might ask, Dan, does it matter that the vertex isn't in the blob? Yeah, it does. It does. That matters a lot, right? Because remember, the way Dijkstra's algorithm works is it picks a vertex to go into the blob because it had the smallest d value, right? So right now we have a scenario where it could have picked y or it could have picked z. So it's going to be important for our setup. Because remember, it's going to incorrectly pick z. That's at least the presumption that we're making here from the way the argument is forming, okay? So we're going to let x be the predecessor of y in P. So for the sake of our algorithm over here, this means that y is equal to the parent of x in the spanning tree that we have. So that's what y is in relation to x. So x is over here. Y is outside the blob. And it must be, this is the case at that time. It's at that time that this is the case. Now, I explicitly drew x right here. Why is x in the blob? Well, it's by construction, right? Because I told you that y is the first vertex in P starting from S to Z that is not in the blob, right? So it means the one that precedes it in the path has to be in the blob. So observe, by construction, x is in the blob. Likewise, remember that z is the first incorrectly picked vertex, right? But remember, x is in the blob, right? X is in the blob. So it means that Dijkstra had to have picked correctly such that if I look at the d value of x, it had to have matched the shortest path distance, right? That's what it means. Since z is the first incorrectly picked vertex, it must be that x dot d, so if I look at the d value for x, it has to be exactly equal to the distance from S to x. This is very important for the setup of this. But yeah, so now we're going to see what we could do with that information. Now we know that x dot d is equal to the distance from S to x, right? When x joined the blob, blob B, regardless if an edge relaxation occurs or not, for vertex y. That means I'm relaxing the edge or I'm not to y. At that time, it has to be the following. At that time, y dot d has to be less than or equal to x dot d plus the weight from x to y. But what's this? what's this? Well, x dot d is just the distance from S to x, right? And I'm just going to keep this, the way to y. I'm just simplifying it a little bit. Since I know this, I'm just going to put that in there. Now, notice that y is next on the path P from x. Then it has to be what? What has to be true about y dot d then? Y dot d has to be, if this is the case, y dot d is in fact the distance from S to y. But here's the catch. Remember back to what I just drew over here. Remember that z is the one that first gets incorrectly picked. Y isn't in the blob, so the algorithm chooses z instead of y. So what does that mean about the d value of z versus the d value of y? It always picks the smallest d value, right? That's what Dijkstra's algorithm over here does. The one that isn't in the blob with the smallest d value. However, z joins the blob B before y. Which means what? What does it mean about their d values under this assumption? It's z dot d has to be less than or equal to y dot d, right? That has to be true because I pick z first. I pick it before y. So that's an important thing to observe about Dijkstra's algorithm. We always pick the one that has a smaller d value. Now this is where we're going to bring up a property that we had before from earlier, where we showed that if I give you a shortest, say, ST path, that if I look at a subpath in the shortest ST path, that subpath also has to be a shortest one with respect to its ends. So we're going to use that property now. I mentioned it was a key ingredient. This is where we're going to use it. Vertex, note it now, vertex, sorry, it just looks like it's melting a little bit. Now, vertex y is along the shortest SZ path. Remember, it's right here. So I have x, y here, and then z's over there, right? So it's along the shortest path. So that means I should be able to decompose the path. So I have a subpath. So watch this. So by our lemma, remember that's the one that says that a subpath of a shortest path is also a shortest path. So by our lemma, the distance from S to Y plus the distance from Y to Z is equal to the distance from S to Z. So I'm going to use two ingredients here. I'm going to star this first one here, the one that says Z dot D is less or equal to Y dot D, and I'm going to double star this one. Now, this is where the part about the edge weights being non-negative is going to be critical in this proof. Since all the edge weights of G are non-negative, for those that are more formally inclined, that means that each, if I give you an edge E, the weight of that edge is greater or equal to 0. It has to be, since they're all non-negative, remember that means that the distance I travel either stays put or I move forwards. I never go backwards. That means the distance from Y to Z. So if I were to go from Y to Z, it has to be greater or equal to 0, right? If I wanted to go from here to there, it has to be greater or equal to 0, right? it doesn't go backwards or something like that. The edge weights are 0 or greater. So combining star and double star, here's what we get. Z dot D is indeed less than or equal to Y dot D, right? That's what that says over there. Now, we know that Y dot D equals the distance from S to Y. But what's this less, like, can I find something that bounds this nicely? Well, surely the distance from S to Y will, because it's equal to it. But remember, the distance from Y to Z, if I want to go from Y to Z, it's going to be along this path P, right? It's going to be along that path. And it's non-negative. So it means it's either going to make this value, if I added in the distance from Y to Z, it's always going to make it the same value or larger, right? But what's this? The distance from S to Y, then plus the distance from Y to Z. What is that? Remember, these are two subpaths. I've combined them into one longer path. That is, they're going to be the distance of, it's the distance of P, right? It's the distance from S to Z, though. So for those that remember, pull out the thing that you had behind your ear. Pull it out. Pull it out. What did we say before? We said Z dot D is greater than the distance from S to Z, right? But this says that the distance, so Z dot D is less than or equal to the distance from S to Z. Therefore, both Z dot D is greater than the distance from S to Z, and Z dot D is less than or equal to the distance from S to Z, yielding a contradiction. Z can't exist. You can't have both those two things simultaneously. So such a Z can't exist, because it would have to be that it's both that its distance is larger, its D value is larger than the shortest distance, but it's also less than or equal to the shortest distance. So you might look at this and say, Dan, what does this proof mean? So it means that if you had a mismatch between the two, I could show you how it would make a bunch of nonsense, right? So you could go through conceivably this process over and over again, and you'll notice that the one it always picks is the one that is closest to the source every single time. That's what Dijkstra does. So from this, since we know we're producing a spanning tree, and every single time from our observation, when we take out a vertex from the priority queue, it joins the blob. The theorem says that when we do this, the D value it has, using the edge that we extend to this given vertex, when it joins the blob, its D value matches the distance from S to that vertex. So as a corollary to all of this, we get the correctness of the algorithm. So the corollary is given a weighted connected undirected graph, G is equal to VE, where the weight of E is greater or equal to 0, where it's non-negative, for all edges. Dijkstra's algorithm Dijkstra's algorithm produces a shortest path tree of S. So this is how this is one way to establish the correctness of Dijkstra's algorithm. And it all boils down to the key idea that we had from before, is that we have a very lazy blob.